Welcome to Group 10's presentation on the pure bending laboratory experiment. Today we are exploring the bending stiffness and strength of structural members using a classic 3-point bending test. For this experiment, our specimen was a mild steel rectangular hollow section or RHS beam. Our analysis relies on the Euler-Bernoulli beam theory, which relates bending stress, moment, geometry, elastic modulus, and curvature into a single equation. A key principle here is that the maximum bending stress always occurs at the extreme fibers. In other words, the very top and the bottom edges of the beam, furthest from the neutral axis, experience the most stress. The test was performed on a hydraulic transverse testing machine. We positioned our 638mm beam onto two outer roller supports, creating an effective span of 538mm. A concentrated load was applied exactly at the mid-span. We gradually increased the downward force, and the machine automatically recorded the load and the mid-span deflection. The beam reached a peak load of 8.3 kilonewtons. At the maximum limit, a 1.0 mm crack formed directly on the tension face, which is the bottom of the beam, right at the midspan, exactly where the theory predicts the highest tensile stress is. When we calculated the experimental modulus of elasticity, we found it to be 58.16 gigapascals, a massive 70.9% error compared to the theoretical 200 gigapascals of mild steel. Why did this happen, if we ask? The primary reason was local contact deformation. Because our hollow beam had a very thin 1mm walls, the loading roller caused local crushing and flattening at the contact point. This created extra downward displacement not accounted for by the standard beam equations. Despite this discrepancy, the test successfully verified the linear elastic behavior and the location of maximum stress under pure bending. Thank you for watching.